Okay guys, sorry for the little technical interruption there to the video, but let's pick up with the MTHFR enzyme. So MTHFR, as I said, is an enzyme. It is called methylene tetrahydrofolate reductase, or we say MTHFR for short. Its job is to take that dietary B9 or folic acid and convert it to an active form your body can use, which we call 5-methyl tetrahydrofolate, or in short 5-MTHF. That's what you will see on your supplements. When we make the conversion to active B9, that can enter that methionine cycle, that gear all the way to the right, and it can help us make the conversion of homocysteine to methionine to SAMe. If I backed up for just a minute, this is it again. To get the active B9 here at the intersection of the gears and turn the pathway from methionine to SAMe to homocysteine and keep it running. That is how we make our methyl groups. That's how we keep homocysteine out of our blood. So what would it mean to have a mutation of that enzyme? Like, who would have that? What is the risk for that? What do you do about that? How do we test for that? That's what we're going to next. So if you have a mutation at that particular enzyme, we call that a genetic SNP, a single nucleotide polymorphism, which means you have a single change in a DNA sequence that will impair that gene's ability to function. It doesn't mean that the MTHFR enzyme is completely inactive. It means that it has a reduced ability to function when you have a mutation. So normal genes, there's two genes that we study for that. The main two genes with all the research that are affecting the MTHFR activity is the C677C and the A1298A. I'm going to back up to the pathway one more time because this is important. The 677 is the one that turns the cycle this way and helps move you into the methionine cycle. The 1298 turns the cycle counterclockwise into the neurotransmitter cycle. If you need the analytical data where that's located on your chromosomes, there you go. There's a science validity. Now, when you have a mutation, again, it has one change, a single nucleotide change. So when you look at a gene and you have the number 677, you have a nucleotide on the front and a nucleotide indicated on the back. C is for cytosine, T is for thymine. When you have a normal MTHFR gene at 677, you have the cytosine, 677 cytosine. If you have a mutation at one of those, so one cytosine on the back end turns to thymine, we would say that you have a heterozygous mutation, meaning just one. But if both the nucleotide front and back were mutated, we would say you had a homozygous mutation, or two mutations. Obviously, two mutations is going to affect the function of the enzyme in a more negative fashion than one would. So this is what we know. This is the science, and this is why you'd want to know, is if you have one mutation, a heterozygous mutation at the 677 gene, that MTHFR enzyme is going to work at a 40% less capacity. So that means you're only getting 60% function out of that enzyme. And if you had the double mutation, the homozygous mutation, you could have a 70% loss of function. I mean, it's only working at 30%. Let me tell you about the combination mutations. Of course, you could have one at the 677 and the 1298. If you had one mutation at each, you would have a 50% loss of function. If you had two mutations at one of them, one at the other, then you would have a 70% loss. So the amount of impairment of that enzyme depends on how many mutations you have on your genetic testing. So let me break that down into an easy to understand way. So something that is toxic to your body is mercury, and everybody knows mercury is in tuna. Well, let's just pick a random number and say tuna had 10 parts of mercury in the can. How many parts of mercury do you want to excrete and get out of your body? 10 parts. You want to get all of it out. You don't want to store any of that mercury. So if you had a normally functioning methylation cycle and you could detox properly, you would get rid of 10 units. But let's say you have an impairment because you had a mutation. And let's say you had the one mutation, so you had a 40% loss. That means it's only working at 60% effectiveness. That means that out of the 10 units of mercury you ate, your body is able to get rid of 6 of them, but you keep 4. And where do you keep them? Well, you store them. You store them in your bone, your brain, your fat tissue, your spleen. And if you had the double mutation, you'd have 70% loss. So out of every 10 units of mercury you ate out of that can of tuna, you would keep 7 and only excrete 3. So you can see the value of understanding how to run your methylation cycle to detox. Now, look, we live in a toxic world, high stress world. We stay stressed out emotionally, physically, financially. Even if you did not have any of these mutations, you are hard pressed with the amount of stress and toxins and infections in your life. You are hard pressed to be able to produce that many methyl groups and get all these toxins out of your body. But if you have a mutation that affects your ability, impairs your ability to make those methyl groups, it is near impossible to think you're going to get all the toxins in your environment out of your body. They're going to get stored, and over time, they're likely going to lead to symptoms and health challenges. So, how common is it? Who should be worried about this? Well, I started the whole lecture with saying 52% of you struggle with this and don't even know it. That means half of every room I give this lecture to, half of those people have this MTHFR mutation at least one level. 44% of you have at least one level. The other 8% seems to have the double mutation. So